What we're witnessing here is SolidCAM's iMachining 3D technology, and it's revolutionizing how manufacturers approach rough machining. Now here's what makes this fascinating. Traditional CAM software calculates toolpaths in straight lines and arcs, which sounds logical until you realize your cutting tool is constantly accelerating and decelerating. That's hard on the machine, hard on the tool, and frankly, slow. iMachining 3D takes a completely different approach. It uses something called morphing spiral technology, maintaining a constant cutting load throughout the entire operation. Watch how the tool moves through this workpiece. See that smooth, flowing pattern? The software is continuously calculating the optimal engagement angle between the tool and material. Instead of taking heavy cuts in easy areas and light cuts in tight corners, it maintains consistent chip thickness. This means your spindle isn't working overtime one moment and coasting the next. The folks at SolidCAM developed this by studying the physics of metal cutting at a level most of us haven't thought about since engineering school. They're monitoring radial chip thinning, adjusting feed rates in real-time calculations, and optimizing the entire spiral path before the first chip flies. What's the real-world result? Manufacturers report cycle time reductions of 50 to 70% compared to conventional roughing strategies. Tool life often doubles or triples because you're not shocking the cutting edge with inconsistent loads. For job shops running tight margins, that's the difference between profit and loss. This is modern manufacturing intelligence at work, turning what used to take all afternoon into a morning job. There's something timeless about forging, isn't there? The fundamental process hasn't changed since blacksmiths were shoeing horses, but the scale and precision certainly have. What Dero Steel is doing here represents the pinnacle of modern forging technology applied to truly massive components. Let's walk through what you're seeing. That glowing ingot started as a carefully selected steel billet, heated in a gas-fired furnace to approximately 2,300 degrees Fahrenheit. At that temperature, the steel's crystalline structure becomes plastic enough to shape. But here's the critical part. It has to stay within a specific temperature window. Too hot and you risk burning the grain structure. Too cold and you'll crack the piece. Notice the manipulator holding that workpiece. This isn't your grandfather's tongs and anvil. These hydraulic manipulators can position components weighing several tons with millimeter precision. The operator is working in concert with the forge press, which can deliver anywhere from 5,000 to 15,000 tons of force, depending on the size of the component. Watch the sequence here. The first blow is what we call an edging pass, redistributing material and beginning to eliminate the ingot's cast structure. Each subsequent strike is carefully planned. The forging engineer has mapped out this entire sequence, calculating how the metal will flow, where it needs to go, and how many heats the piece can withstand before the grain structure is optimized. Between passes, you'll see them rotating and repositioning the workpiece. This ensures uniform compression throughout the component. That's crucial because forging isn't just about achieving a shape, it's about refining the internal grain structure, eliminating voids, and creating directional strength exactly where the finished part needs it. This particular component might end up in a power generation facility, a large marine vessel, or heavy industrial equipment. These forged pieces often serve for decades, which is why this process, refined over generations, remains irreplaceable for critical applications. What you're watching here is a beautiful example of how far automated manufacturing has come. Nide's motor assembly line represents the kind of precision and repeatability that would have seemed like science fiction just a generation ago. Let's start at the beginning of this process. That robotic arm is handling the stator core, which is the stationary part of the electric motor. Now, inserting copper windings into a stator used to be a skilled manual operation requiring patience and steady hands. Notice how this automated needle winding system feeds wire through each slot with perfect tension and placement. The robot positions the stator, and specialized needles insert and form the windings in a choreographed sequence that takes seconds per coil. Moving down the line, you're seeing the rotor assembly station. The rotor shaft, lamination stack, and end rings must align within tolerances measured in hundredths of a millimeter. The vision system you see mounted above uses high-resolution cameras to verify positioning before the hydraulic press seats everything together. If something's off by even a fraction, the system stops and alerts the operator. Here's what's particularly clever about NIDE's approach. Each motor is being built with its own digital record. As components move through assembly, sensors and cameras are documenting measurements, verifying torque values on every fastener, and tracking which specific parts went into which motor. The balancing station you're seeing now is critical. Even a slight imbalance in the rotor causes vibration, noise, and premature bearing wear. The machine spins the rotor, measures vibration, calculates exactly where to remove tiny amounts of material, and then precisely mills those correction points. The final automated testing station energizes each motor, measures current draw, checks rotation, and verifies performance specifications. Any motor that doesn't meet parameters gets flagged for manual inspection. This level of automation doesn't eliminate skilled workers. It elevates them to oversight and problem-solving roles while ensuring every motor meets exacting standards. Watch this Faxon RCMI 280 section bender at work on an IPE 400 beam. The RCMI 280 can handle beams up to 11 inches tall, applying controlled pressure through 3 rolls arranged in a pyramid configuration. The bottom rolls are driven, feeding the beam through, while the top roll applies downward pressure to create the bend. The operator can adjust the radius by changing how far that top roll descends. What's impressive is the consistency. Feed this machine identical beams with the same settings, and you'll get identical curves every time. Kiel Steel's facility showcases several forging techniques that have been perfected over decades. Let's break down what you're observing across these operations. First, we're looking at open die forging. Unlike closed die forging, where metal is pressed into a specific mold cavity, open die uses flat or simple-shaped dies to manipulate the workpiece. That glowing billet is being compressed between dies, but notice how the operator keeps repositioning it. Each strike elongates and shapes the metal incrementally. This technique dates back centuries, but the hydraulic presses and precise temperature control make it far more sophisticated than traditional hammer forging. Open die is particularly valuable for large components where creating a custom die would be cost prohibitive, or when you need the superior grain structure that multiple working passes create. Now we're seeing ring rolling, which is absolutely mesmerizing once you understand what's happening. That heated ring blank is being fed between rollers that are simultaneously compressing and expanding it. The main roll applies pressure, reducing the ring's wall thickness, and as the metal has to go somewhere, the ring grows in diameter. It's like rolling out pie dough, except the dough is glowing steel at 2000 degrees. The beautiful part is how the grain structure flows circumferentially, creating a ring with exceptional strength in the direction it needs it most. These rings often become bearings, flanges, or pressure vessel components. The hammer forging you're witnessing here uses a different principle. Instead of slow, sustained pressure like a hydraulic press, a forging hammer delivers rapid, repeated blows. That pneumatic or mechanical hammer is striking dozens of times per minute. Each impact work hardens the surface while allowing the heat to redistribute between blows. This technique excels at creating complex shapes and achieving specific surface characteristics. The operator's skill really shines here. They're reading the color of the steel, feeling how it's responding, and adjusting their approach based on decades of experience. What ties all these techniques together is metallurgical knowledge. Forging isn't just shaping metal, It's refining its internal structure, aligning grain boundaries, eliminating porosity, and creating mechanical properties that cast or machined parts simply cannot match. The temperature windows, the amount of working, the cooling rates, every variable affects the final product's strength, toughness, and reliability. Steel drums might seem simple. Just metal containers, right? But the manufacturing process you're watching here involves some genuinely clever engineering and precision metalworking that's been refined over more than a century. We start with steel coil stock, typically 14 to 18 gauge, depending on the drum's intended use. That first station is a blanking press, cutting circular blanks that will become the drum ends. Notice the precision. These aren't just rough circles. The edges are clean, the diameter exact, because when you're seaming a drum lid, tolerances matter. The body formation is particularly interesting. That flat steel sheet is being fed into a roll-forming machine that gradually curves it into a cylinder. This isn't a single bend, it's a progressive curve through multiple roller stations, each adding a bit more curvature. This gradual approach prevents the metal from work hardening too quickly or developing stress fractures. At the final station, the edges meet and feed into a seam welder that creates a continuous, leak-proof joint down the drum's length. Now watch the beading operation. Those horizontal ribs you see being rolled into the drum body aren't decorative. They're structural reinforcements that dramatically increase the drum's resistance to denting and buckling. The beading machine uses rotating wheels that press grooves into the cylinder as it rotates. Each bead effectively creates a stiffening ring, similar to how corrugation strengthens cardboard. The end seaming process is where precision really counts. The drum body and the end cap come together at a seaming station where rollers progressively fold and compress the two pieces of metal together, creating what's called a double seam. This mechanical joint is so well designed that it's often stronger than the surrounding metal. Getting this right requires exact alignment and the correct amount of compression. Too loose and it leaks, too tight and you weaken the metal. Finally, there's coating and finishing. Most drums receive an internal coating to prevent corrosion or contamination, and an external finish for protection and identification. The spray application you're seeing ensures even coverage, followed by a baking oven that cures the coating. What's remarkable is the speed. Modern drum manufacturing lines can produce hundreds of drums per hour, each one meeting strict specifications for capacity, strength, and leak resistance.